Part A is a bond enthalpy question, which just asks you to calculate delta H for this reaction. All of these substances are gases, so you can do that using bond enthalpies, and that's then going to form the basis for the rest of the question. A fair number of people treated this as a Hess's law kind of question and drew out a Hess's law cycle. You can do that in principle if you treat the gaseous atoms as the intermediate stage, but it was very noticeable that the great majority of people who did that ended up getting the signs all muddled up. So I think the pragmatic answer is that it's best to treat bond enthalpy questions as a different sort of method from Hess's law questions, because it seems to then be sort of more reliable in terms of getting the signs right. So what we said, remember, was that the best thing to do is to rewrite the equation showing the displayed formulae, because then you can keep track of all of the bonds and make sure you don't miscount them. So 2SO2 becomes that, plus 2H2O is this, gives you 2H2S. And it's a little bit laborious, but it does have the huge virtue that you're going to be absolutely certain that you don't miscount the bonds if you do this. So it's up to you, but that's a suggestion. So then what we learnt to do was to make a separate total of all of the bonds on the left, which have to be broken, and then all of the bonds on the right, which are going to be formed. So we can write down bonds broken. And we've got 1, 2, 3, 4. Tick them off like that so that you don't miscount them. 4 times S double bond O, which is 4 times 523. And then we've got 1, 2, 3, 4 OH bonds, which is 4 times 463. And that's all there is on the left hand side. And if you add up that lot, you get 3944 kilojoules per mole. So if you broke all of the bonds in the reactants, which indeed in this case you are going to have to do, that's the amount of energy that has to be put in. So then we make a separate subtotal, which is the bonds formed in the products on the right hand side. And again, go through the same method. So we've got 1, 2, 3, 4 times HS, which is 4 times 339. And we've got 1, 2, 3 times OO. So that's 3 times 495. And if we add that lot up, we get 2841 kilojoules per mole. So then we just have to do the subtraction. And the commonest mistake is getting the sign wrong, because you forget which one's positive and which one's negative. But you shouldn't do that, because you know that breaking bonds always requires energy to be put in. Bond breaking is always endothermic, and endothermic is positive. So if you learn those basic things, you don't get the signs wrong. Okay, so this is bond breaking. All these bonds have to be destroyed, so that's going to be endothermic. So we get that delta H is plus 3944. It's the endothermic contribution. But we're making these bonds, so that's exothermic, which is negative, so minus 2841. And that comes to plus 1103 kilojoules per mole. You shouldn't really just write 1103. You might get away with it, and they'll assume you mean plus, but really delta H should always have an explicit sign, positive or negative. So plus 1103 kilojoules per mole. Okay, so part B then is where we introduce Le Chatelier's principle. So remember, this is just a rule. It's not really something that you have to understand, because it's not really sort of about scientific understanding. It's just a rule of thumb that this French guy, Le Chatelier, came up with. But it's actually incredibly useful and powerful, because it's always right. And what he said was that whatever change you make to the conditions, affecting an equilibrium, then the equilibrium will shift in the direction that opposes that change, that tries to counteract the change that you've made. So in part B, it's talking about the fact that when these volcanic gases being carried up in the magma, when they reach the surface, the temperature suddenly drops. And so the question is, which way will this equilibrium shift in response to that temperature drop? So we know that it's endothermic going forward because we've worked that out in part 1. It's plus 1103 going forwards, and therefore it's minus 1103 going backwards. So if it reaches the surface and it cools down, its response is going to be to try and heat it up again. And how do you heat it up? Well, you go in the exothermic direction, because exothermic reactions give out heat and will therefore tend to warm things up again. So that's what you say, that the equilibrium shifts in the exothermic direction to oppose the decrease in temperature. And you can see that makes sense, that exothermic reaction gives out heat, so that will oppose the fact that the temperature has decreased. But then you have to spell out which direction that is. Well, remember, exothermic is negative, so that means it will shift to the left. You can either say shift to the left, or you can say shift in the backward direction. That one's safer if you have left-right issues. So that means that it will shift in the backward direction. But you can't just leave it there, because the question didn't say which direction will it shift in. It said what will happen to the ratio of SO2 to H2S. So you can see if it shifted in the backward direction, you're going to get more SO2 and less H2S. So you can say that, or you can say that the SO2 to H2S ratio increases. Okay, but I think most people just did it like this, and that was fine. So more SO2, less H2S will be the consequence. So that's all you do with Le Chatelier. It's just a very simple rule. You don't want to overthink it, because it is just a rule. It's not about deep understanding. Okay, so that's part B. Okay, so part C wants yet another enthalpy profile diagram, but this one is a little bit different because it's endothermic in the forward direction, which the ones you did earlier in the exercise were not. So we've got enthalpy here, we've got 2SO2 plus 2H2O are our left-hand side reactants there. Sorry, that's gas, not liquid. It's steam, not liquid water. And it's endothermic going forwards, which means that we're going to a higher enthalpy level. It's a positive delta H. So it's got to look like this. So we have 2H2S plus 3O2 up there. And that, and a one-way arrow going from there to the right-hand side, is plus 1103, because it asks for the numerical value, so it's plus 1103 kilojoules per mole there. So then we have to put the activation energies on. So again, it's this idea that there's a pathway that leads from SO2 and steam to H2S and oxygen, and that pathway involves going over this energy barrier here. So as we said before, the best way to keep these diagrams uncluttered is just to draw these energy levels like this, and to say, right, and this one as well. Now, the activation energy for the forward reaction is going from here to the top of the hill. Okay, so the activation energy for the forward direction is how much extra energy you have to add on to the average energy of the reactants to reach this critical value at the top of the hill. So the activation energy for the forward reaction is that. And it tells you in the question that that has a value of plus 1460. Now the activation energy for the reverse reaction means starting from here, this is the right hand side, the reverse reaction goes back to there over the same barrier. So the activation energy for the reverse reaction starts from the right hand side mixture, which is here, up to the same hilltop. So this is the activation energy in the backward direction. And on this diagram you can see sort of visually very easily what that is, because it's just the difference between plus 1460, which is that big change, and plus 1103, which is that. The alternative is just to learn the general relationship, which is that delta H is equal to the forward activation energy minus the reverse one. And if you just memorize that relationship, if the sort of visual thinking doesn't really help you, then you can just learn that relationship and just rearrange it to get that EA reverse is equal to EA forward minus delta H, which is plus 1460 minus 1103, which is plus 357 kilojoules per mole. So you can do it sort of algebraically like that, but as I say, I think it's kind of just more obvious looking at the diagram to say, well, if 1103 plus that adds up to this overall change, then that's going to be plus 357. Goes on there. Temperature is not the only thing that's going to change when the volcanic gases in the magma reach the surface, because once they're, the constraints of the volume of the magma chamber are released, then the pressure is going to decrease very dramatically. And we know that Le Chatelier tells you that these equilibria can also respond to pressure. If you count up, there are 4 moles of gas on the left hand side and 5 moles of gas on the right hand side. So if the pressure decreases, which is what happens when it reaches the surface, Le Chatelier tells you that it will try to oppose that, and it will oppose it by moving in the direction where there are more moles of gas, because the more moles of gas, the more pressure. So simple prediction is that when the pressure decreases, this will shift to the right to create more moles of gas and therefore oppose the change. When you're explaining it, make sure you talk about moles of gas, not just moles, because they can catch you out by putting some reactants which are solids or liquids into this, and then obviously they don't have the same effect on the pressure. So it's moles of gas that we're talking about. So the answer is that the equilibrium shifts to the right to oppose a decrease in pressure, because there are more moles of gas on the right. And again, you can do it in terms of forward and backward directions. If you want to say it shifts in the forward direction, because there are that generates more moles of gas, so you can avoid the left-right if that causes you problems. And again, make sure you answer the question. It doesn't just say which way does it shift, it says what happens to the ratio of SO2 to H2S. So that means there will be less SO2 and more H2S. Part E introduces yet another thing that's going to result when the gases reach the surface, which is that they're going to mix with air. And of course air contains oxygen, which is part of the equilibrium. So whenever you change the amount of any one of these substances, that's going to shift the equilibrium to oppose the change. So mixing with air is increasing the amount of oxygen in the mixture, and that's going to drive the equilibrium backwards to oppose that change, to use up oxygen and oppose that change, and therefore we're going to get more SO2 and less H2S. Okay, so it's yet another thing that's changing once these gases reach the surface. Okay, so the equilibrium shifts in the backward direction or to the left. You can put it either way. To oppose. Always use this language of opposing the change, to oppose the increase in oxygen concentration. And again, relate that to what's going on in terms of the actual amounts of substance. So more SO2 and less H2S will result from that. So finally, part F is really just bringing these things together. You can see that we've now got 3 separate predictions of what might happen as a result of these volcanic gases reaching the surface. In terms of the temperature change, we predict that the cooling would be opposed by moving in the exothermic direction, which is backwards. So the temperature the temperature decrease suggested that we would get more SO2. But the pressure decrease suggested that it would move in the other way to create more moles of gas, and that would give you less SO2 and more H2S. And finally, the effect of oxygen is again to give you more SO2. So you can see the problem, that you've got 3 separate predictions, all consequences of this mixture of gases reaching the surface. And because Le Chatelier is just a qualitative predictor, it doesn't tell you how much it will shift in response to any one of these things. So there's no way it can tell you which one of these effects is going to be biggest. So you don't know whether the shift to the right, driven by the pressure change, or the shift to the left, driven by the oxygen and by the temperature change. You don't know which of those is going to be bigger, so you can't predict what the overall change would be. Okay, so you can say that different factors changing predict opposing shifts in the equilibrium, and we can't tell which will be bigger. So we can't tell what the overall direction of change will be.